Alright, so in this video we're going to derive the Laplace transforms for cosine of omega t and sine of omega t. Alright, so I like to use the coefficient of t inside there to be the variable, or just the parameter omega. And I'm going to do this using the fact that we know that cosine and sine of omega t solve an appropriate initial value problem. This can also be done, as I've noted at the top of this, using the definition of Laplace transform. Alright, and I'm just going to direct you where you could see that done. So two places. One, if you go to this section in Lumen, and if you look at my written notes, alright, that on the 5th page of that starting, I actually go through and use the definition of Laplace transform. You have to use integration by parts twice, alright, and then that will give us the result. Okay, so you can look through the details there if you so wish to check those out. Alright, so again, it's a little bit of calculation. Alright, a similar thing is done in this last video by James Sousa. Alright, and he does an example where he computes the Laplace transform of sine of 6t, but the manipulations are very much the same. Alright, that's one way to look at it. Now we're going to do it a little differently by showing that because cosine and sine solve an appropriate initial value problem, that combined with some facts about the Laplace transform and differentiation, which we're getting more used to now, will lead us to the formula. Alright, and after we derive the formula once, we're just going to use that time and again, alright, to solve differential equations. So we're going to start with cosine of omega t. First thing to note is, based on our work from before, and you can check this out, cosine of omega t solves this initial value problem here, that y double prime plus omega squared times y is 0, and y of 0 is 1, y prime of 0 is equal 1. I'll quick go through that check. If I take the first derivative, it's going to be negative. We got to pop out a factor of omega using the chain rule times sine of omega t. The second derivative will be, we're going to get another factor of omega coming out, so negative omega squared times cosine of omega t. So the second derivative is negative omega times cosine, and then if the original therefore is just cosine of omega t, if we multiply that by omega squared and then add it to the second derivative, it will give us 0. And notice if you plug 0 into cosine of omega t, you're going to get cosine of 0, which is 1. If you plug 0 into the first derivative, which is sine negative omega times sine of omega t, you get sine of 0, which is 0. So it solves this initial value problem here. Now what we're going to do is we're going to take the Laplace transform of this differential equation, alright, using the term-by-term linearity of the Laplace transform, and then also this fact about how the Laplace transform works with its second derivative. Alright, so we're going to get the Laplace transform of the second derivative plus, now omega is a constant, we can pull that factor out, times the Laplace transform of y is going to equal the Laplace transform of 0. Alright, and the Laplace transform of 0 is 0. So the right-hand side is 0. Now, substitute in the fact about second derivatives in the Laplace transform. That's going to tell us then that we've got s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0 plus omega squared times the Laplace transform of y is going to equal 0. Now, what is y of 0? Y of 0 is 1. Y prime of 0, from the fact up above, is 0. So substituting those quantities in now, and then combining the like terms here on the left side, we can factor out the Laplace transform of y from those two terms, and what we are left with is s squared plus omega squared, and then minus s equals 0. Alright, and we're just about actually done with this derivation. All we need to do now is just notice that we can add s to both sides of this equation, and then we want to isolate the Laplace transform of y. So doing that, we get s squared plus omega squared times the Laplace transform of y is equal to s. Alright, and then just isolate by doing the division. So divide both sides by s squared times s squared plus omega squared, and that's going to tell us that the Laplace transform of y, or y of t, is equal to s over s squared plus omega squared. Now all we need to do to finish this derivation up is to realize that what did we start out with? What was y of t? Or what is y of t? What is the solution to this differential equation? Y of t is actually cosine of t, cosine of omega t. So since that solves the differential equation, we know that y is equal cosine of omega t. That gives us our fact. The Laplace transform of cosine of omega t is equal to s, the variable s, over the variable s squared plus the number omega squared in the denominator. All right, so that's a fact that we're going to use, and we're going to go through a similar derivation for the Laplace transform of sine. So we'll do that on the next page. All right, so very similar, and then we have these in the table listed as well for reference. But we don't have to compute that by hand anymore. But let's just do one quick example before we get to the Laplace transform of sine. So for instance, if we had, just a quick example here, the Laplace transform of cosine of, let's say, 4t. What is that going to be? It's s over s squared plus 4 squared would give me 16. Okay. All right, and then we're going to do sine next. All right, so we now know the Laplace transform for cosine. Now we're going to learn the Laplace transform for sine. For this one, it satisfies the same differential equation, as we can check, but a little different initial condition. All right, and I'll leave that check to you if you want to do that. So we're going to go through the same derivation then by taking the Laplace transform of this differential equation, plugging in the initial conditions, and then using the fact that sine solves it, that y of t is equal to sine of omega t actually, that will give us the formula. So let's go through the same manipulations. So we're going to get the Laplace transform of the second derivative plus omega squared, again doing term by term application, times the Laplace transform of y is going to equal the Laplace transform of 0, which is 0. Now applying the second derivative fact for the first term, we get, as before, s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0, and then the other terms are the same. And now let's substitute in the initial conditions. Y of 0 was 0 this time. Y prime of 0 is omega. So that's a little different than what we saw in the previous work for cosine. All right, now this term is 0, so let's get rid of that one. Let's factor out the Laplace transform to combine these two terms together. So that will give us s squared plus omega squared times the Laplace transform of y minus s equals 0. And then simply we're just going to add the s over and then divide. So we just have s on this side, and then to isolate the Laplace transform, we'll just do the division. So we get Laplace transform of y is equal s over s squared plus omega squared. All right, now keeping in mind again, what was y of t? It was sine of omega t. All right, again, that solves the differential equation. And the process we just went through was the same process we're going to go through for solving initial value problems, but in those ones we're going to be inverting. Here we actually know what y is, so we can just actually substitute it in, and it's going to give us an important fact. So the Laplace transform of sine of omega t is equal to s over s squared plus omega squared. We'll just do a quick example, and then we'll look at that in the table, and that will be it for this video. So again, just a quick example of this. What's the Laplace transform of sine of, let's say, 2t? That will be, this time it's s on top, the variable s. I got a mistake here that I need to fix. Alright, it's a good learning experience here, but I went too quickly, and I need to fix it, and let's fix it now. So s was what I had in my mind from the previous video. What should this s have actually been? It should have been omega. I had it in the previous step, so we're going to get omega here. Alright, now when we add that over, this should not be s here, this should be omega. All right, and then when we add that over and then divide, we end up getting omega on top. Okay, so sorry about that, but we fixed it now. Alright, so what is the Laplace transform of sine of omega t? The difference in the formula, the denominator stays the same. The difference is in the numerator. For cosine, we have s on top. For sine, we have omega on top. And then we have s squared plus omega squared on the bottom. So if we have sine of 2t, we should have omega on top, which is 2. And then the denominator is going to be sine, or s squared, plus 2 squared, which is 4. Okay. All right, now let's just take a look at that in the table. Okay, so again, just to recap, I had a small error there, which we just fixed. We substituted in the initial condition y prime of 0 was omega, and then I accidentally changed that omega to s. So now I fixed it, and then that tells us the Laplace transform of sine of omega t is omega over s squared plus omega squared. And if you look at my table of Laplace transforms, right, that I'm going to be sharing with you, that I've got that in that table. Cosine of omega t is s over s squared plus omega squared, and sine is omega over s squared plus omega squared. So again, just notice the difference in the formula and the similarity. The denominator is exactly the same. For cosine, you get s on top. For sine, you get omega on top.